All right, let's get started. So today we'll talk mostly about various kinds of scheduling, various aspects of scheduling, and also various types of schedulers, so to speak. But first, maybe there might be some questions about the midterm. Any questions? All right, let me put it a different way. Now that you've read all of the code, all the stuff that we talked about, are there any pieces of the code that you feel you didn't understand? Anything in particular? Okay. Interesting question. So, thank you. The question was, we talked about process switching on a single CPU, but what happens when you have more than one CPU at the same time? And so, this varies a little bit between operating systems. x86 is relatively primitive in that sense. So there's a single list of processes in x86, and all the CPUs share it. So they will run through the list and look for one that's runnable. A process that is currently running is already taken, so you can't schedule that one on your CPU. So you continue looking until you find a runnable one, and then you start running that one. And because of this p-table lock, only one CPU at a time will be traversing the list. Yeah, all the CPUs run the same code, or they run the same kernel code that is in different processes. And in the case of x86, processes could very easily be moving back and forth between CPUs. In principle, that's a bad idea because of memory locality. You want to be reusing the memory that's in the cache. So at least in Linux, there's actually two levels of schedulers. There's a short-term and a long-term scheduler. The short-term scheduler looks exactly like, or very much like x86 in this regard. There's one CPU that owns, let's see. There's one short-term scheduler per CPU. So they each have a list of processes that is responsible for that core is responsible for. The long-term scheduler, which I think operates more on a sort of second time scale, perhaps 10-second time scale, we'll look at the load on each core and see, oh, that one's working really hard. This one's mostly just spinning in the scheduler trying to find something to do. And so it'll rebalance, it'll move a process over from one CPU to another CPU over the longer term, like that. On average, you want to have roughly even load on the CPUs, right? But if you move it all the time, then you get poor performance on everything. So there's a trade-off there. Other questions? Yeah, the midterm is on Thursday, right? It's in class, and it'll be all class. Don't forget to bring your source code. Okay, so in that case, we'll talk a little bit more about scheduling today. So we discussed how you kind of switch between processes, but that's about it. We talked about the mechanics of switching from one process to another. Today we'll dig into a little bit how to pick which process to switch to, and also when to switch, and how to deal with that. So perhaps as a first step, let's think about what we want out of a scheduler. I think we probably want efficiency. All right, perhaps in two senses. We don't spend too much time scheduling. All right, doing the actual scheduling work. This probably want to minimize that. Of course, if it really helps make everything else better, then we can spend some extra effort, right? But we shouldn't spend a large part of our CPU on scheduling work. Okay, and also we want to don't wait too much. All right. So if we're running an I/O bound program, once we start waiting for a disk, for example, we probably ought to do something else if we can. Or perhaps we'd call this instead maximize parallelism. So we'll call that, okay, let's do it like this. Maximize parallelism, and that kind of means two things. It's don't spin wait for I/O. Like if we're waiting for some other part of the machine to do something, well, then we really ought to see if there's something else we can do in the scheduler. But you can also turn this around. You could say when I/O is ready, we really ought to react to it immediately. Why is that a good idea? What do you think? What's the benefit of immediately reacting to when the disk is ready, for example? Disk has taken its really long time and it's read a sector. It returns a sector, like it says, the sector is ready through an interrupt. Then what? Why should we wait? Well, we should do it immediately.
So that the next process that needs to access it can do it as soon as possible as well.
Exactly. So that now we've done one of these slow I/O operations, we really ought to start the disk doing the next one, if there's something more that needs to be done. Or if we're waiting for something that's even slower than I/O, a user, right, then we want to give the user an interactive behavior experience. It should feel like the computer is always reacting to whatever I'm doing immediately. Right? So don't delay responding to I/O, or minimize latency. Is there anything else we want from a scheduler you can think of? So a scheduler is the piece of software that decides which program to run next, right? Yeah. Fairness, exactly. Yeah, very good. So one can argue about what's fair. I mean, fair sounds like a relatively sort of high judgment word here. Like it's, or what's the term for it? It's kind of, there's some values involved in what's fair and what's not. Like, but in some very technical term, we may want to say provide the same amount of resources to every process. Now, is that fair? Maybe the process isn't so important, so it shouldn't get as much, or it didn't try as hard, so it shouldn't get as much if you're thinking politics, right? But generally, there ought to be some degree of distribution of resources among our processes. So there's at least one. Okay, so let's think about a couple. You can say equal distribution, equal sharing of resources. So is this a good fairness policy? You have a few programs, they all get about as much of the CPU. Actually, let's just call it CPU. Really, there are other resources. There's the I/O that needs to be scheduled. There's cache memory that needs to be shared. There is this. Let's see. There's just memory, RAM in general. You have to decide who gets to be a victim. When you need to evict something. But let's talk just about CPU for now. So there's one way to do it. Is that a sort of a desirable goal?
If there's processes that spend all their time just waiting and only on for a slight bit of time, you're never going to get equal sharing.
Right. Okay. Good. So we have some processes that are I/O bound, some that are CPU bound. I guess those are the two main ones. Like I/O, if we include the user in I/O, then I think those are the two main types. So it doesn't much make much sense to say, yeah, this program that's just waiting for the user should have as much CPU as this program that needs the CPU all the time. Okay, so let's try the other one. Right? So that's another way you can divide resources up, of course, but it's hard to tell what need is for programs, especially for CPU-bound programs. So you have two CPU-bound programs. They can't really express the need, I suppose, so they probably ought to get about as much, right? If they're just equally demanding. Okay, so maybe this applies best to CPU-bound programs. There's also this thing called prioritization, where you think this is an important program, here's a less important program. Let's see, let's do that separately. Priorities. Need to be able to probably provide more resources to important programs. High priority programs. Oops. Or perhaps lower latency. Right? Why don't we say more CPU time? All right. I think that sort of covers it. Okay. No, this part is in the fairness category. There's one that's relatively popular. It's called max-min fairness. So max-min means we should maximize the let's see. Actually, maybe describe it the other way around. So whoever is suffering the most should get resources next. Right. So some process got the minimum amount of resources at the moment. For whatever reason, that's the one we should maximize next. So we should give that the CPU next. Of course, if a program doesn't want the CPU, it's not really in that calculation. All right. So in order to at least get to this seems like probably the first step. In order to have anything sensible, and this is also sort of the level we're at with XV6. In order to have anything sensible here, at the very least, we ought to not have our processes running while they're waiting for I/O. So let's just see how that works first. Just see which branch I'm on. Oh, master. Very good. All right. So we haven't really been dealing with disk I/O yet, so let's take a look at console. Console I/O is waiting for the user, very simple. There isn't really much for a process to do while the user is waiting to hit enter. At least if I remember correctly, this is how it works in the... I don't know if it's enter, actually. We'll have to find out. Does the process wake up every time you hit a key, or does it wake up only when you hit enter? I'm not sure. So let's take a look at that. But basically, the way we come into all this is in sysfile. It'll be sysread, which then goes to file read. There. And in this case, it's console. It's a file. Right? Console is just a file that's on disk, but it's one of those device files, so it's not quite the same as a normal disk file. But either way, it's an FDI node. It's not a pipe. So we'll go through read I, and this is probably somewhat familiar. And let's see. And inside of read I, there's a dev thing that we ran into before, and this one I can't follow automatically, but that'll go to console read. Oh. Okay, so we're looking through this buffer. We see, and it's actually a circular buffer, we see while there isn't anything in the buffer, so if the read pointer is the same as the write pointer, that means there's nothing, the buffer is currently empty. So now if we got killed along the way, then we should just quit, fine. Otherwise, we sleep, and this is sort of the key to getting this I/O wait to be a proper queue wait as opposed to spinning for and waiting for the input. So here we could, in principle, just not have this sleep. We're just having a wait, so we could just spin on this until it changes. And that would actually work just fine. All right? Because at some point a timer will go off, timer interrupt, and then our handler in trap will decide, oh, time to switch processes. And so we're switching out of this context into the interrupt, and then we're currently still in the same process, right? But then we decide it's time to switch processes, so now we go through that, the switch.s, and we're out running something else for a while. And eventually we come back and we keep spinning around this one. And hopefully by then we have some input. But then we spent a lot of time just going around here, waiting for that timer interrupt. So the better solution is the sleep. So sleep just takes the process out of the scheduler. So it says here, I'm sleeping. So now the scheduler, whenever it tries to find a process, it looks for one that's runnable. But now the process is in state sleeping, so it won't run again. It will never run again until that changes. And we say, what are we sleeping until, so to speak? What are we waiting for here? And then finally we switch to the scheduler, and we'll never come back here. Oh, we will come back here eventually, but it'll take us a while. All right. So now at least nothing's happening, so how do we get it back into running again? All right. So then we have to look at the other side. Now the user is hitting a keyboard, and we go through the keyboard interrupt. Actually, always best to look at the code, I find. So here's the interrupt handling. Here's the keyboard interrupt. See what happens at a keyboard interrupt. Oh, it goes straight to a console interrupt. And in there we say, okay, let's read the next character, it looks like. What is this get C here? Probably here. Oh. Oh, it was passed in. Oh, very good. That's what happened. Thank you. Keyboard get C. Right, very good. And keyboard get C is here. Right. Okay. So we got an interrupt, but the interrupt just says, okay, something happened on the keyboard. All right. And then it's up to us to figure out what was it that happened on the keyboard. We ask the keyboard this way with the in B and out B, same as any other driver essentially. And now the keyboard is kind of a complicated device. There are all these modifier things, and so we have to kind of figure out this combination of keys. What does that actually mean in terms of what character we should put in the buffer? And that's what's going on here. So we're translating some keyboard information into a character. Okay, so we pass that to console interrupt. I suppose, in fact, I don't suppose, I know that it's done this way because the console can also take input from the serial port. You may have used this standard I/O kind of thing that you can do on the command line. So you can type on the command line in Linux instead of in your emulator. Who's tried that? Okay, yeah, a couple of you. It's nice because it's a little bit annoying, the normal QEMU window. It goes something like, actually let me see if I can find it. There it is. So minus serial standard IO. Not like that. Right. So now I have my x86 on that console, and Control C just kills it. Very nice.
That's so nice.
Save you some pain for the rest of the semester. And by the way, if you didn't notice, I hit Control R, and then I said standard IO because I couldn't remember exactly what it was. That's a reverse search in my command history in any bash. But definitely stuff you want to remember. Okay. Going back to what's going on in our machine. So you could have a serial port interrupt. I think it's called UART, right? In which case we would call console interrupt with a different get character because it comes a different way over a serial port than it does from a keyboard. So this is just a nice way of structuring it so that the shared structure, or the shared code for our console interrupt handling is in one place. Actually, let's just back up, see how that works. UART interrupt is right there, and here's our UART interrupt handler code, which just takes a character off the serial port. Much easier with a serial port because it comes as characters, it doesn't come as key codes. All right, backing up, back into the keyboard interrupt. All right. So what are we doing here? We're reading the one character, and then we decide what we should be doing. Okay, let's say it's a normal character. Then it's one of these. So now we're storing the character into the array, and this is just a clever circular buffer logic that we don't really need to worry too much about. Put it out on the screen. That's our conf put C, so that then goes to CGA put C or UART put C, probably both. And then, and here it is. Okay, so if we hit new line or Control D, which is end of file, then, and if, let's see, what was this E versus the R? I don't remember. Aha, okay, so E is sort of a temporary write, it looks like. That's where you fill stuff into the buffer, but the W says what is readable by the user process, I think. Probably. Yeah, this is where we're putting stuff in.
This is read index, edit index.
Edit index, I see, yeah. Yeah, so basically, we're only updating the W when we hit Control N or Control D. When you hit the new line or Control D. So the process can never see the characters until you hit Enter, right? That would be the point. Okay, and then we wake up whoever's waiting for this input. And this was the channel that we specified in our wait. So let's see what wake up's doing. It calls wake up 1. We talked about this pattern before where you sometimes acquire the lock, and in other places you don't have to acquire the lock. So there's the wake up and a wake up 1. There's more of those. So here, finally, to wake up whoever's waiting with that number, we had or was it called sleep, perhaps? Whoever has a sleep with a certain number is now going to turn from sleeping to state runnable. And then the next time the scheduler is run, well, then we probably will start this process running again. So through this process, then or through all these steps, the end effect is if you're waiting for I/O, you're never spinning on the CPU. And that's our first step to having reasonable efficiency. Now, unfortunately, XV6, if we don't have any other programs, XV6 is just spinning in the scheduler instead. So it's not that it's that much more efficient. But in principle, we could have multiple processes running in XV6. It's easy enough, just start them up. It's just that we don't have many useful programs that do that in this little OS. Okay, so we have it running. We have something working with I/O. Now, how do we get to a somewhat fair distribution of our CPU resources? Let's see what we're looking for here. Okay, so we got this one. This is our sleep wait function. Let's see, what's that called actually? It's called a queue. Oh, just say that. So that takes the process out of the scheduler until the I/O is done. Okay, let's see. How do we do this then? Don't delay responding to I/O. What would be a good way to fix that? So now I'm running a heavy process. Someone hits a key on the keyboard, and really now the whoever's waiting for the keyboard should get that character right away. What do we need to do to make that happen?
In this trap, where you trap on keyboard, handle a switch if you need to.
Right. So we get some new input from we get an I/O event, assuming that I/O events are higher priority, right? Whatever we're processing at the moment is not some super urgent thing that needs to continue processing. Then what we need to do is identify who was waiting for this and switch to that process.
Is this called preemption?
No, preemption is or preemptive multitasking. Oh, preemption means all sorts of things, right? Preemptive multitasking, at least, is where the timer goes off frequently and just switches them. The alternative to preemptive multitasking is cooperative multitasking, where the process on its own yields the CPU. There's sort of a little hybrid between the two, where you might say any system call is an opportunity to switch, right? Because then the process has sort of yielded the CPU to the kernel code, and the kernel can do what it wants. But without a timer and without any other external interrupts, it gets really hard to do multitasking, at least if you have a process that isn't behaving right. Okay, so actually that's maybe let's preemption. Okay, so usually using a timer. Okay, that's actually, one could say that this is part of the scheduler. I guess it depends on your definition of a scheduler. But I don't know, did we talk about, what about if we don't have a timer? No? So I would say that you can implement preemptive multitasking without a timer. But how would you do that? So the definition of preemptive multitasking is the process does not yield the CPU. We have a while true loop, right? It's just spinning. There's no system calls or anything that kind of gives the kernel an opportunity to switch. So now how do we get to switch programs anyway, switch processes anyway?
Is that button, the physical button?
Yeah, we did talk about it. All right. So it triggers some other interrupt. It's a little silly to do it with a button, right? But now, if you need to work this, if you need this to work in some system where there really aren't any timer interrupts, well, you could consider using, say, the disk. So you could do a read request, and then when the read comes back, well, you have another timer interrupt, or not a timer. You get another interrupt from the disk, right? So during the time of the reading, then the process can do whatever it wants, and you know you're going to get control back when the read finishes. Right? You just issue another read and another read. It's one way to do it. You can co-op disks for all sorts of stuff. When I was a kid, we were playing with the disk motors to make them be a speaker. You go, that was kind of fun at the time. Anyway, so what's next? Right. I think let's worry about efficiency while we discuss the sort of the desired other goals of the scheduler. So let's see. To get to fairness, we need somehow to be able to split the CPU here. And I think a problem that we have is that processes, they behave in all sorts of different ways. So you'll have some processes that do a little bit of work and then do some I/O. A little bit of work, do some I/O. You have others that do a lot of system calls. You have others that don't do any system calls at all. And then we want them all to kind of get some sort of fair treatment in the scheduler. So let's see about some fairness alternatives, implementations of scheduling fairness. You know, actually, before we get there, there's some other kinds of schedulers that we maybe should be aware of too. It's called a batch scheduler. So if you know the jobs that you need to run, you know you have like these 10 jobs, the first few will take only a little bit of time, and then there's this other one that will take a really long time. Now the question is, in which order should you run them? Right? Or you say, this one is really important, that one is not so important, in which order do you run them? It's not multitasking, it's just run the one to completion and then the next one. This used to be a thing on old computers, and it still survives in some OS textbooks, not in ours, I think. But it is very relevant for, say, factories and that sort of thing. So in there you have, let's see, I'll just briefly mention those. You'll have things like a FIFO, first in, first out scheduler. This is kind of typical. You provide a job, whoever got in first into the queue gets to run next. And then, so this one is very easy to implement and is relatively fair. Maybe it's not the most efficient by all measures. There's another one that's called a LIFO, last in, first out. This one has some surprising benefits. So usually you worry about the throughput of a scheduler. It's the same in both. You worry about the latency. How long is it going to take to finish a job? It's actually much better for LIFO. So FIFO always has latency that is sort of the length of the queue. But for LIFO, essentially you enter the queue and you get right back out. But unfortunately, it has some problems with starvation. There's also some jobs that just never get done. If you're really busy, they never get done. So if you want to maximize the number of jobs you get out, well, I guess neither of those are very good. If you want to minimize latency and you don't care about things finishing, that's actually a perfectly fine way to do things. If you're, say, your customer, or in this case, let's see, what's a good example? I don't have a good computer science example, but say you are printing textbooks, right? And so now you either have a very long queue, and by the time you've printed the textbook, the new revision is already out, because they always make a new revision, so people have to buy new textbooks. But if you have a very long queue, you're a printer, by the time you print the last book in the queue, it's already gotten old. And so if you do a FIFO, you do only useless work. If you do a LIFO, then at least the stuff you got in, you get it out quickly, and it's valuable work. And then, well, some people lost out, and that's too bad. There's also shortest job first, which is really great if you want to minimize the mean latency of a job. Oh, this guy is usually really quick when I ask for something, right? But if you ask for something long, it'll take forever. It's also a kind of a fine policy. There's lots of things you can do in batch schedulers that you just can't do in a real-time scheduler, because in a batch scheduler, you know how long it's going to take. There's deadline scheduling, where you can reject jobs because you know it's going to take too long, and so on. When we're just scheduling on the fly, we don't know how long the program's going to run. And usually that's the case. In most computer systems, we have no idea how long it's going to run or what it's going to do next. So we kind of have to look at the history of what's happened so far and make a determination from there. So let's look at our current scheduler first. It's a round robin. So if we have, this is actually what's current x86 scheduler. With round robin scheduling, your process runs until either another process yields the CPU explicitly or until the timer goes off, and then we take the next one in a list. And we go down the list, and then we start from the top, round and around. That's it. If we have only, say, CPU bound processes, this actually provides good fairness. Right, we're going to run the first one for one tick, right, one time slot, and then the next one for a time slot, and then we go around, and it's going to be completely fair. Perfectly fair for CPU-bound processes. So that's great. It has a problem with the I/O. So the x86 scheduler does not respect I/O. Right? It has the sleep and the wait, but the sleep and the wake up. But what happens when we wake a process up? Well, we just make it runnable, and then we forget about it. And so it could well be that we're running this process now, right? And the process we woke up was the one just above in the list. So now we have to go through hundreds of milliseconds of other processes until we get to run this I/O bound process. So that's really not nice. Not at all good for I/O. And there's also no prioritization. There's no way to express that this process should run twice as often or should run first or anything like that in a round robin scheduling. Okay, so another thing we could do is called weighted round robin. So here, instead of just going around the list, some processes get more than one entry. You can think of it that way at least. We can't just have a process table or go around the list. We'd have to have sort of a separate schedule table that says which process ID to run next, or in accordance with our schedule. But you can say if we have 3 processes, you could say go 1, 2, 3, 1, 2, 1, like that. Could be our schedule. Actually, let me let's put a 3 in there. So now we see that the 1 is twice as important as the 2 and the 3, that it gets twice as much of the CPU. That's really nice. I think the general form of this is called generalized processor sharing. Okay, now let's back this up a little bit. We'll go the other way around. Okay, so if we want to have fairness, it'd be nice if we could say each CPU gets a fraction, each process gets a fraction of the CPU, and we can specify any fraction we want. Now this schedule I just provided is a little bit coarser than that. The weighted round robin schedule with the schedule entries, you could go twice as important, but you can't be 15% more important unless you have a very long array of the schedule, and making up that schedule could get complicated. Yeah?
This is somewhat off topic, but you said the XV6 is round robin scheduling, right?
Yes.
And we said we want to minimize the latency for
Mm-hmm.
operations, so it doesn't really do that.
No, XV6 does a very poor job of that. Yeah. Generally, XV6 is not built for performance at all. It's built for teaching. But it is also used for research a whole lot, I might add. In part because you learn about it in class, maybe 1 or 2 OS classes, and you come up with some ideas, and you can immediately see how you would build it in XV6 because you know the whole OS. But if you try to do it in Linux,
You break everything else.
yeah, it'll take you forever. And not only will it take you forever, but by the time you're done with forever, now Linux has moved on. And so now you have to integrate all the patches from a million other people into yours. And in the end, it's very hard to get something done in Linux research-wise. Of course, if you're in industry, you just add more resources, and generally it works. But it would have to be something really important. Right, okay, so generalized processor sharing says we should be able to get any sort of fraction of the CPU to each process. We just provide this weight, saying how much each one of them should get. I guess the method I provided, so weighted round robin scheduling in general, we could probably make a large schedule like that, or we can come up with some other way to do it. One of them is called deficit round robin. Let's see. Okay, so I don't actually know how you would implement weighted round robin without this repeating schedule. Deficit round robin is a different way to do it. So here you say each process has a weight. That's the weight from the generalized processor sharing. And then you go through the list, and every time a process runs, you add some cost to the sort of the total spending of the process. So each process has a weight and a balance. Let's call it a balance. Oh, we should call it a deficit. Balance is good. Okay. So now you run your process, and then, assuming you don't end early or anything like that for now, we would just say, okay, add the weight to the balance at the end of each slot. Okay, and so now the sort of the end game here is, which process do we pick next? We don't go around and around. That doesn't really do anything but the weight. Instead, we have to pick one process to run, and it'll be the one with the smallest balance. So you spent some time on the CPU, now you have a larger balance. Someone else didn't spend so much time, they have a smaller balance, or they were more important, so they had a smaller weight. It should be inversely proportional to the weight. Inversely proportional to the priority. Yes?
That's what I was going to
Oh, okay, yeah. Right. So now if you spend a time slot and you are really important, you get like a 0.1 added to your balance. If you're not so important, then you get a 1.0 added to it. So it's going to take a while before you get to run again. So this in general provides this generalized processor sharing. If we ignore the whole bit about interrupts and I/O and such. Okay. Now the problem, I suppose, with this one is we have to pull out a process, like we have to take the lowest cost process or the lowest balance process out, and so that's going to be a log n operation in a number of processes. We use a heap probably for it, but we can live with that. All right, let's see if we have some other methods. Yeah, so here's, I guess this doesn't take care of our I/O at all. Or does it? Yeah, it does take care of the I/O relatively well. So this is actually very, very close to what is done in Linux. So now let's think about I/O. So we are waiting for I/O. While we're waiting, nothing's getting added to our balance. So we get a lower and lower, well, everyone else gets a higher and higher balance. We get a low one, and then the keyboard interrupt comes in, and we're woken up, and now suddenly we have the lowest balance. So we can spend as long as we want on the CPU, essentially, and we immediately get to handle the interrupt. Does make things a little weird, though. So now you could imagine. So the question is that fair? Okay.
After that operation, the I/O operation turns, it'll still have a lower balance. So it might continue running that same process for like the next 10 slots.
Yeah, exactly. So I guess the question is it fair that a process that's been around for a long time and just waited has a smaller balance than a process that just started up and just waited? Let's see. Oh yeah, that's one. I guess that's. Let's put it a different way. Okay, so the problem that we had here was the process was waiting for I/O for a long time, and it sort of accumulated this credit and is now able to run for a long time on the CPU, potentially making everything jerky, right? Because now no other process gets to run. So if you're running a game or something, and you had a little program in the background was waiting for some network input, now suddenly it's hogging the CPU for a few seconds. That's not really that great. Maybe put even more simply, your balance, when you start a program, presumably the balance is 0. So now, and that program hasn't been around. All the other programs have been running for a year, at least on some of my machines. So now this new program is starting up. Should it get the whole CPU for a year equivalent, to make up? Doesn't seem quite fair. Right? So what should the balance be of this new program? The minimum of all the others, right? So that means it gets to the sort of the front of the queue, but it doesn't have this huge balance that it can spend. And probably the same is true for an I/O bound program, right? If you
Sorry, I was going to ask the same about, but that does not answer for I/O.
right. But so if you've been sitting there waiting for a long time, you probably should not get to have a super low balance. Right? It's probably better to make it the minimum of all the other programs in the current run queue. So that way it's at the front. But again, if it's an I/O bound program, it shouldn't need a whole lot of CPU time. So probably it'll finish in that slot and then go back to waiting again. Normally it would work that way, I think. I suppose for a good scheduler, you don't want it to sort of, there shouldn't be a way to trick it to kind of slow down the machine when you want to. And you could imagine nefarious programs trying to do some sort of denial of service attack on a machine they have access to, and it'd be better if they couldn't really affect the performance of the machine. So what about if you've used the CPU a lot, and now you wait for I/O suddenly, and the I/O comes? You should probably not get the minimum, right? If you have a large balance, you should probably keep your large balance, I suppose. Just because you're waiting for I/O now, that doesn't mean you're necessarily an I/O button program. It just happened the one time.
So would you say the max of the current and then compare that against the min of the others?
Yeah, that sounds right. Let's see.
So you have the min of the others and then take the max of that value with its current weight. Right.
This won't work?
I mean, not sure. I was saying that if you're taking the max between those two and if the process has been waiting for a long time, then to be the balance will still be higher than the minimum, right? At least.
So
If
you're
it's
saying-
been waiting for a long time, then it has a small balance.
Oh, yeah, sorry.
Right. And so that should be okay. Oh, not current weight, current balance, right? I think we have to think about these balances as in credit card balances and not bank account balances, right? Yeah.
But if we still keep its like high balance, how would we make it run right away to like handle I/O?
Yeah. So I guess there's always some trade-off here, but a process that has accumulated a large balance probably shouldn't suddenly lose it all just because it waited for a little bit of I/O. Right?
I mean, is it really possible to accrue a significantly larger balance than all the other processes anyway? Because if it's starting to gain a balance, it's going to run all the other ones first. So it can only be at most like one of its own cycles out of the range of the others. So otherwise the other ones would have let that happen.
Good point. If they were all waiting, they would get the same balance as you had anyway.
Right.
Yeah, so maybe you can't run off all that far, assuming we are doing this deficit round robin thing. Yeah. So probably in the end, maybe this isn't so important. Like this doing the max of the two because there's not such a big difference. Yeah.
This might be a little more, I guess, like a technical question, but like if the balance is like always increasing, right, is there a chance like it's gonna overflow eventually? How do they handle that? Like
That's a good one. So I think the way they handle it in Linux is you just subtract the minimum off. I am not, let's see, trying to remember what they did now.
The current process is larger than a certain number, and it is then subtract them in, because then you can compare every time instead of subtracting every time.
So they had a clever way. There's a clever way that does it continuously. But what is it?
Do they store like an offset size or something maybe?
You know, it doesn't matter anymore. There used to be one in 32-bit, and I don't. It's probably there somewhere still in Linux, but in 64-bit it doesn't really matter because the numbers you can store in a 64-bit register are so large that you would run for 1,000 years, and you know nobody cares then at that point. Probably they have some handling for it. I'm not sure. Just to make sure we get the math right, So the finest granularity we can have for the clock is 1 cycle. Doesn't make any sense to have less than that. It probably should be more than that, but let's call it 1 cycle. The highest CPU frequency out there, probably, let's call it 4 gigahertz. You know, I might say 4 gigahertz because that's 4 billion, which is 2 to the power 32. So that's half our size already. So roughly then, 32 bits gives us 1 second, right? But now we have 32 seconds left, 32 bits left. That's 4 billion seconds. How many is that? Let's ask Google. What? Oh. 136 years. Okay, I can believe that. There it is. All right, 126 years, yeah. Maybe you had a 2 to the power of, yeah. Okay, so 126 years. That's a little less than I had expected. Probably because Linux doesn't deal with cycles, naturally. Probably what we want is a larger granularity than that, but I'm not sure what the right granularity would be. That's what they're doing. Okay, it's the same as cycles, essentially. So, So in that case, they must have a handling, some sort of handling in there, because you know there's going to be some machine that's running now that is still running 126 years from now. So we wouldn't want it to crash then.
Y2K 100.
Yeah, exactly. I don't know, maybe you've heard of, there's a, is it 2026 or something? And was that?
38.
38, is it?
Yeah.
Yeah.
Unix epoch.
The Unix epoch time, right. There's another Y2K coming. Expect a large employment boom. And,
This one's probably going to be even worse though, right?
maybe. We'll see.
I mean, this is like number of bits is 19 whatever.
1970.
Yeah.
Yeah, so basically roughly when Unix was created, they started the timer and it's running out. We'll see. We still have some time. What is it, 20 years? Yeah. Probably will be fine. Okay, so in Linux then, what actually goes on is something very similar to this deficit round robin. So they keep basically a heap of all processes, and as a process runs, well, okay, so you pick a process being the one with the smallest balance. But then when a process comes back and yields the CPU, they calculate how long did you actually spend on the CPU. Because you can imagine a process that does a lot of yielding, but that uses the CPU a lot still. Okay, this is called the Linux CFS, Completely Fair Scheduler. And I think some people have issues with the completely fair part, but it's still a very good one. So this is a per process, per thread scheduler. There's something called, if you want more, there's something called C groups in Linux that where you can specify that all these threads belong to the same group. They should all get this much of the CPU. There's all sorts of extra levels of policy in here, like all this C group should only have together at most 128 megs of RAM, you know, and you can add and remove processes and so on. There's a lot of stuff going on there, but sort of the high-level picture is that we have a scheduler. Let's see, one CFS scheduler per core. And this one independently, modulo the C group stuff, schedules the threads based on their balance. So runs the lowest balance thread first. And there's a slot time or an interrupt, timer interrupt interval called a tick, I think. No, that's not it actually. Don't know what it's called because ticks is specifically for the Unix epoch time. Is 1 millisecond, sometimes 10 milliseconds. So now the timer goes off. It figures out, oh, how long did the previous CPU actually, the previous process actually spend on the CPU? So maybe we switched processes for some other reason. It wasn't the timer that went off last time. Someone yielded the CPU, but the timer goes off regularly anyway. So when the timer goes off, then calculate actual time spent on the CPU and add to the balance multiplied by a weight. So this weight here is between 0 and 1. If you have a 0, you're really high priority because you can spend a lot of time on the CPU and it doesn't cost you anything. Right? And then, okay, so we basically pay as much as we used, pay for as much as we used, and then we get put back in the heap. And then you pull out the next, the lowest element in the heap, and it may very well be the process that we just ran. If so, well, in either case, we run the one that's at the top of the heap. And that's pretty much it. Yeah.
So would you still use a heap if the one at the top is not necessarily runnable? Then how would you get the second min?
Ah, okay. So very good. Runnable processes kept in a heap. Okay. And now when a state, let's see, when a process, okay, I should call this threads. When a thread is added, is woken up. So balance equals, I think it'll go like that. So this way, if you have been waiting for I/O, well, now you're probably going to be at the front of the queue. And this is a nice trade-off here, because a properly I/O bound process will always have a low balance. Right? They're not spending a lot of time on the CPU. If you're somewhere in between I/O bound and CPU bound, well, you shouldn't really benefit from your I/O operations. And if you're CPU bound, then clearly it doesn't matter what you're doing with I/O. Yeah. Okay. So that's the per thread scheduler. And then long-term scheduler does load balancing between CPUs. So here we're moving processes between per CPU schedulers. Long time interval to minimize overhead. All right. So the cost of moving a process is, well, there's a couple here. One is if you want to remove if you're a different CPU and you want to remove a process from some other other CPU scheduler, you'll have to acquire a lock on it. So now you're stopping the other CPU from even accessing its schedule. And that's a little problematic if you're doing it often. And of course, the other one is if you move a process over, probably the process had some things in the cache, and those cache entries will now be useless because you're on the wrong CPU. Yep.
So does this mean there's like one master CPU?
No.
Okay.
The long-term scheduler, I believe, runs on every CPU. I'm not sure, actually. I'll have to look that up. It could just as well be a process that can run on just a process like any other. That seems more likely, to be honest.
If it's running at the same time on different CPUs, then there will be synchronization problems, right?
So you still have to acquire a lock, right? Or you could imagine you could imagine clever schemes where you don't interfere with the scheduler of a CPU, but you say you add to a queue to be added to the scheduler. There's different ways to avoid synchronization issues. Yeah.
And also, if that long-term scheduler is just a normal process, you can just give it a really large weight so that it'll just by itself in the short-term scheduler get procced every once in a while.
It won't be determined.
Oh yeah, right. Yeah. No, but he was saying that you can't. The long-term scheduler can't just go and modify the thread local, the CPU local schedules without acquiring a lock. Right. Okay. So then there's the C groups that also kind of impact this. That says, oh, you can't run on these 3 CPUs, or these 4 processes must run on one of those 5 CPUs, and all sorts of fancy options there. But this is a general idea. So I think in x86 we have sort of a very special purpose scheduler, in the sense that we have the scheduler runs continuously. It doesn't make a decision. Right? It just runs the for loop. We switch into and out of the scheduler, and it just continues taking the next one. We couldn't implement almost any of these things. Yeah, the only thing we can do really is the round robin schedule with that approach. Normally, I think you would switch to, like, you would run a scheduler every time. Instead, you would say, oh, let's make a decision on what to run next. We run a scheduler function, you come back and you say this is the process to run. So our sort of a more typical scheduler would look like this: while true, find process, and then switch to process, right? Like that. This is not what the x86 scheduler does. So here we're kind of running across all of the processes every time, one way or another, to decide which one to run next. I suspect every other scheduler you'll see is going to be more like that. But still, we're switching sort of out of here and then back into here and go around and then the next. Find the next process. All right. What are we missing? Oh, there are more subtleties with the long-term scheduler. I don't know. Has anyone ever heard the term NUMA aware? It stands for non-uniform memory access. So on a modern system, it doesn't always take the same amount of time to access memory from access different addresses in your memory. And a NUMA-aware scheduler is generally for this kind of design where you have, let's see, that's good. So let's have a couple of sockets. Socket is where you plug in your CPU on a motherboard. This whole white sheet is the motherboard. And then we have some DRAM. Let's call it RAM. Sitting in a bank over here. This is actually what a motherboard would look like. There's a bus that goes like this. Whoop. and a bus like that. But this CPU can't directly access this RAM. Generally, what you have instead is an interconnect between these two. And so if this CPU wants to access an address that's over here, and that could be split up in any number of ways. But let's say just address 0 through 4 gigabytes is here, and 4 gigabytes through 8 gigabytes is up here. Then if you want to read address 6 gigabytes, you would have to ask the memory controller on this CPU to get it for you. And not only that, but inside of each of these sockets, we usually have a few cores. Sometimes more than a few. On our systems, it's 16 cores or 32 threads with hyper-threading. And so now, these 4 can talk quickly to each other through a shared cache, the level 3 cache. So now you're trying to make some, your process is running on here. Everything's in your L1 cache, but also in the L3 that's shared between all of them. So now it's cheap to switch from here to there. But if you were to switch from here to over there, it gets really expensive. Because now this whole, whatever's sitting in the L3 cache, would have to move over, and nothing was kind of hot on this side. So a NUMA-aware scheduler would be careful to not move between sockets unless really necessary, and then would move maybe not so memory-intensive processes and this sort of thing. So there's a lot going on. It all depends on what applications you want to run. Of course, in the Linux scheduler, they have no idea. So they try to make a compromise between something running Apache servers and something wanting to be interactive on a desktop, and find something that sort of works across the board. One thing that I've seen, I don't remember the details, was basically they use these C groups to say, oh, all of this appears on the display. Right? This interacts with an actual user, so all of these should be higher priority. That sort of thing can sort of help a little bit. But I think if you're working on a very specific system, which some of you may be in the future, perhaps a scheduler for a self-driving car, or for a drone, or for a space probe, something like that, where actual real-time performance really matters, then probably you'll want to think carefully about which scheduler you're using, or implement your own scheduler to fit the particular application. So we're talking mostly about general purpose sort of schedulers here, but there's a lot that can be done just at the scheduler level. So that's something to keep an eye out for. And again, unless you know operating systems, you can't touch that stuff. So makes you a little special. Questions?
Does the same principle apply for the same socket? Like maybe that's why most motherboards are color-coded for their DRAM slots?
Let's see. Does the same principle what?
So where the RAMs are on a bus for a different actual thing.
So, okay, let's take a picture of a motherboard. Crap. Find a better one. Oh, I was going for shopping. Let's do images. Here. Okay, so you're talking about this sort of thing.
Yeah, where they're blue and black. Or
Right. So this is a 2-socket motherboard. And here we can see, well, I guess it's 4, it looks like it's 8 banks of RAM. So each motherboard has a couple of, each socket has usually I've seen 2 memory controllers per socket. So then you would have one controller for this and one controller for that. It'll be better to have put half your sticks here and half your sticks there, so that you spread the load across the 2 controllers. Now, why these are color coded, that must be some some internal piece with to do with the memory controller that I'm not aware of. Probably there's channels in there too, one way or another. But yeah, generally this actual physical layout is what decides the performance in the end. You'll have half of the cores inside of here, and this one doesn't have an actual chip on it, but half of the cores on the chip would be closer to these, physically closer to this amount of RAM, and that actually matters for the performance in the end. So you want to try to distribute it, both the RAM and the processors evenly, so you make the best use of your hardware. I am thinking of offering, perhaps in the fall, next fall, a class on concurrent systems, like high performance programming for this sort of thing. If that sounds interesting, keep an eye out. It'll be probably a 498 or whatever it's called, perhaps in the fall. Okay, that's it for today. So we'll have the midterm on Thursday, don't forget, and the homework is due the Thursday after that.